Welcome to the Explainer, everyone. If you've been tracking the bleeding edge of AI lately, you've probably realized we're hitting a wall. We're hitting the limits of what a single, rigidly prompted model can actually do. So today, we're diving into a massive, frankly incredible paradigm shift. We're talking about the leap from static, heavily constrained AI loops to truly autonomous, self-evolving agents that are actually capable of open-ended scientific discovery. We're unpacking a framework called Coral. Okay, let's dive into this. To really appreciate why Coral is such a game changer, we kind of have to talk about the villain of our story first. Early attempts to string multiple AI agents together, they usually ended in total disaster. Just look at this quote, it hits the nail on the head. When you let agents just chat endlessly in a peer-to-peer setup, it degrades so fast. They end up arguing in circles, their context windows get completely polluted with weird conversational pleasantries and hallucinations. And honestly, they just turn into this chaotic, token-burning mess without solving anything complex. It's literally like putting 10 toddlers in a room and telling them to build a rocket. Lots of noise, zero progress. Right, so historically, to stop that exact chaos, researchers just locked these agents in fixed evolutionary search loops. Think of systems like AlphaEvolve or FunSearch. The algorithm basically acted as this rigid scaffolding, almost like a developmental jail, really. It dictated exactly what the language model was allowed to explore, exactly when it could mutate code, and what it kept. The AI was just a passive engine waiting for instructions. Which brings us to the billion-dollar question. What happens when we break these models out of that jail? What happens when we just hand the keys to the lab over to stateful digital researchers and let them design their own evolution? Here's the roadmap for today's explainer. 1. The end of fixed search. 2. Enter Coral and autonomous agents. 3. The 3 architectural pillars. 4. Safety and process containment. 5. Shattering benchmarks. And 6. Prism theory. We're building from the core problem all the way to some mind-bending theoretical futures, so let's get moving. Section 1. The end of fixed search. Let's start by looking at that massive, fundamental shift in how we actually treat optimization pipelines. And this brilliantly illustrates this stark contrast we're talking about. Over on the left, we've got fixed evolutionary search. In these legacy setups, history is just this static population of programs. Memory gets completely wiped between runs, and a centralized, human-written script calls all the shots. It's rigid, and frankly, it's amnesiac. But on the right, that's the new paradigm. That's Coral. It's all about autonomous, decentralized exploration. These agents are long-running, they share persistent memory, and they execute asynchronously. They aren't just passively generating code, they're actively deciding what to investigate next. Moving to Section 2, enter Coral, autonomous agents. It's time to officially introduce the hero of our story, built by an all-star team from MIT, NSU, Stanford, Meta, and Microsoft. So Coral actually stands for Co-Evolving Agents with Shared Persistent Memory, Asynchronous Execution, and Reflection Algorithm. It's a mouthful, but what it does is completely dismantle that rigid algorithmic scaffolding we were just talking about. It takes us from a vertical, sequential pipeline where agents are stuck in fixed roles to true horizontal scaling. We're talking about an ecosystem where autonomous digital researchers manage their own workspaces, write their own documentation, and synthesize reusable skills entirely on their own terms. Section 3, the 3 architectural pillars. Now, how exactly does it pull this off without instantly reverting to that chaotic, token-burning mess? Well, it all comes down to the engineering. Let's slow down for a second and really unpack the brilliance of the Coral engine. Now, what's really interesting about this slide is how beautifully simple, yet ridiculously powerful the memory structure is. They didn't build some hyper-complex proprietary vector database. No, the shared persistent memory is just a standard Git file system, mapped into each agent's local directory using basic symbolic links. There are 3 root folders. First, the attempts directory. That acts as a decentralized leaderboard of all historical evaluations. Then the notes directory, which is where agents write up markdown reflections, log dead ends, and cross-reference bugs. And finally, skills, a library for highly reusable, validated scripts, like say an auto-batcher to profile memory. Which brings us to a design choice that, honestly, is just pure genius. There is absolutely zero direct message passing in Coral. None. The agents do not talk to each other. Instead, they collaborate implicitly by reading and writing files to that shared Git repository using standard command line tools. By totally bypassing chat, they avoid that dreaded conversational hallucination trap altogether. So if Agent 1 wants to know what Agent 2 is working on, it just filters the leaderboard and reads the markdown file. Simple.
And because they're communicating strictly through the file system, their execution can be entirely asynchronous. This is our second pillar. Every single agent operates in its own isolated workspace, which is basically a complete copy of the target repository. They pick tasks, they run intermediate compilations, and they explore on their own schedule. It's literally like having a team of remote workers in completely different time zones. There is no central micromanager bottlenecking the whole operation. Let's move to and see how this builds into the third pillar, the heartbeat mechanism. You see, left entirely to their own devices, autonomous agents will often get hyper-fixated on micro-optimizations. They essentially get trapped in local minima. So to prevent that, Coral uses a trigger-based system that functions exactly like an operating system interrupt. It goes like this. Every single evaluation triggers a local reflect heartbeat, forcing the agent to analyze the concrete compiler results. Every 10 evaluations, that triggers a global consolidate heartbeat, prompting the agent to step back, scan the whole workspace, and synthesize its findings into the shared notes folder. And if an agent fails to improve for 5 consecutive evaluations, a pivot heartbeat interrupts them. It forces them to totally discard their current approach and start fresh from a new mathematical foundation. It's brilliant. Section 4, Safety and Process Containment. All right, we have to address the elephant in the room here. If you are giving AI agents this much autonomy to write and execute arbitrary code, how on earth do you keep it safe? Well, the security architecture relies on extremely rigorous process isolation. The agents run inside strict sandboxed containers with non-root privileges. But the absolute most vital feature here is evaluator separation. The actual grading code, the script that scores the AI's work, is hidden away in a private directory that the agents cannot access or read. This is absolutely crucial because it prevents the agents from gaming the system or reward hacking the scoring function to just print fake high scores. On top of that, the evaluator runs as an independent child process with a hard timeout, like, say, 300 seconds. So a buggy infinite loop solution can't just hang the entire system indefinitely. Section 5. Shattering the benchmarks. Okay, so with the architecture and the safety rails locked in, what actually happens when you turn this beast on? The quantitative breakthroughs are staggering, so let's look at the scoreboard. 1,103 execution cycles. That is the brand new state-of-the-art score achieved by 4 co-evolving Coral agents on Anthropic's notoriously difficult CUDA-kernel engineering task. So the crucial point is the previous best-known score for that task was 1,363 cycles. Coral dropped it to 1,103. That is a massive 19% reduction in execution cycles on a hardware optimization task that demands incredibly complex, coordinated rewrites. And remember, it achieved this completely autonomously. It had an improvement rate 3 to 10 times higher than fixed evolutionary baselines, using just a fraction of the computational evaluations. To put that into perspective, in the world of hardware optimization, a 19% cycle reduction isn't just a tiny win. It's a massive, game-changing saving in time, compute, and real-world money. And it wasn't just the Anthropic kernel either. Across 11 different tasks spanning intense mathematical and systems optimization, Coral set 8 new state-of-the-art results. For example, on the highly complex Erdos minimum overlap problem, Coral hit record density scores with 10 times faster evolution. Because of that horizontal parallelism, the agents can pursue all these diverse local directions at the same time, organically diffusing successful techniques through their shared memory. It completely pushes the boundaries of what these models can naturally discover. Section 6, Prism and Entropy-Gated Memory. Now, the empirical success of Coral is phenomenal, absolutely. But it also prompted a much deeper, almost philosophical question about how AI systems manage knowledge over long horizons. And that leads us to a really wondrous theoretical advancement. Enter Prism. Prism is an evolutionary memory substrate developed by Suyash Mishra, and it basically formalizes Coral's qualitative folder structure into a rigorous, mathematical, decision-theoretic framework. Because think about it, as agents run for days or even weeks, context window bloat becomes a huge problem. Prism solves this using what's called Shannon entropy-gated layering. It dynamically categorizes memory based on 2 things, its informational entropy and the literal computational token cost to retrieve it. This means the system perfectly balances what to keep top of mind versus what to stash in the archive, entirely solving the context window bloat problem. It stratifies memory into 3 access tiers. Low entropy, high-frequency knowledge, like those validated skills, are super reusable, so they are constantly loaded in the active context window. Medium entropy data, like the notes, are retrieved dynamically via vector searches, but only when they're actually relevant to a specific task. And high entropy data? Those verbose, raw execution logs in the attempts folder, they get archived. The system only accesses them when formal value of information calculations prove that pulling them up is actually worth the token cost. Ultimately, PRISM points us toward a fascinating theoretical peak called evolutionary stable memory sets, or ESMS. This is essentially a mathematical convergence point. Under Bayesian decay and evolutionary selection, the AI's shared memory naturally reaches an optimal, stable equilibrium. It organically learns what to hold on to and gracefully discards the rest. That means the AI's mind doesn't just collapse under its own weight as it runs indefinitely. It becomes self-sustaining and perfectly tuned for ongoing discovery.
Which brings us to the profound implication of this whole paradigm shift. We are no longer just prompting language models to spit out answers. We are literally spinning up digital organizations that manage their own memory, correct their own trajectories, and autonomously shatter state-of-the-art benchmarks in complex engineering. So I want to leave you with this thought. What happens to human engineering when AI agents finally break out of their fixed loops, self-evolve, and start building their own open-ended scientific ecosystems? The jailbreak has happened, and the paradigm has shifted. I hope this explainer helped you grasp exactly how. Keep learning and keep asking the big questions.